Hello everyone! So today we are going to be talking about precipitation reactions. So these are the reactions, the chemical reactions between ions in solution that result in the formation of a solid. So we are going to be applying those solubility rules, figuring out what sort of solid is going to form, and then we are going to write out the formulas in the correct format, and we'll show you some other things that happen as well. So the reaction between aqueous means dissolved, silver nitrate, and aqueous sodium chloride is, so let's identify the ions present and write the formulas of the initial compounds. So the initial compounds are silver nitrate and sodium chloride, so NaCl. And so these are both aqueous. And so this first step, what they're asking is, what is going to be this this reaction? So when we write the word aqueous, we are actually implying that a reaction has been undergone, and that is a dissociation reaction. So an aqueous compound is actually never its formula in the vessel that you're studying or in the reaction mechanism. If it has the aqueous phase, then we are talking about a chemical that is already dissociated. So this is really what aqueous NaCl means. It means that you have a solution. This is, we can kind of, here's my thinking gray. This is my beaker over here. And inside my beaker, I have sodium ions, I have chlorine ions, I have sodium ions, and I have aluminum ions and nitrate ions and silver ions floating around. And if we're talking about them before they've been mixed together, then of course we would have just one of those sets. Now that they're in solution with each other, we have the possibility of chemical reactions between the pairs. So we're going to write the formulas of the two possible compounds formed from the ions. So that means we could have Ag plus aqueous forming with chlorine minus aqueous, and that would give us chemical reaction here. We are headed towards a solubility to an equilibrium sort of situation, so let's put a little equilibrium symbol, and that is going to could make AgCl, and we also could make sodium plus aqueous plus the nitrate, NO3 minus aqueous, and that would give us NaNO3. And we want to do this because sometimes writing these ionic compounds can be a little tricky. So this way, at least, I have a very clear counting up method here. So I know that I need to make my chemicals electrically neutral. So if they both have a minus 1 charge and a plus 1 charge, then in the formula it's going to be a 1-to-1 ratio. So now I'm going to go back and check my solubility rules. One of the solubility rules we know is that chlorine ions are not soluble when combined with silver. So this is a solid. Meanwhile, sodium and nitrate both don't have any requirements on their solubility. They are always soluble with everything. So this would also be aqueous. So what that means in terms of this arrow is that this arrow is a straight up equilibrium. It's the chemical might form, but it might not. And meanwhile, this silver chloride is more or less like this. And in fact, we might even estimate it as being a straightforward one-directional arrow. Like that. So this is insoluble. So that's an insoluble precipitate. Insoluble PPT. So now write the chemical equation and balance it. And so we are going to write out our chemical equation to show the formation of these chemicals. So here we're talking about writing out the AgCl, not AgCl, the starting point, the AgNO3. This is a solution of AgNO3 being added to a solution of sodium chloride, and that is going to be forming some solution of sodium nitrate plus some silver chloride. And we know that one is solid. So we are going to determine which ones of these are going to be, if any of these compounds are that would form precipitate, indicate the precipitate with a solid, and the spectator ions as aqueous. So that's that. We can see our aqueous, we can see our solid here. And so that is fine. I'm a little bit, okay. Yeah, we'll leave it there. Sometimes we would take this a step further and take this to a net ionic equation, which I'm actually surprised is not mentioned here. So let's just write out that net ionic equation right now. So what I want to do is, this is the chemical reaction, or the precipitation reaction. Precipitation reaction. And so if we take in some of the details that we already worked out above, we could also write what is known as an ionic reaction. And in the ionic reaction, we would replace that silver nitrate with its composite ions here. Just cheat a little bit. And replace the sodium, with its composite. Okay. I don't know if this is any faster, but I do kind of want to, I'm more or less doing this so we can kind of think about it like this is where all these values are coming from. And so in this way, we're kind of splitting up. We're thinking about it, hey, this wasn't a solution of sodium chloride, it was a solution of sodium ions and a solution of chlorine ions, all in the same reaction vessel. And then they were getting placed inside of a reaction, they're getting reacted with this other mixture, and the result is not going to be formation of sodium nitrate, but it will be the formation of sodium ions and nitrate ions, because those are aqueous, and the formation of silver chloride, a solid precipitate. So that is an ionic reaction. And if we take this one step further, there is a net ionic reaction available here, where we will cancel out things that are on both sides of the equation. So notice that nitrates are on both sides of the equation. Sodium is on both sides of the equation. So we end up with a final version of this where we are really only talking about a reaction between silver and chlorine, and that forms silver chloride solid. And so that is called a net ionic reaction. It's something that you sometimes come into contact with in your chemistry studies, and it might be relevant for us in the future. One thing to keep in mind here is that this means that the silver and chlorine concentrations are not restricted to being from the sodium chloride or from the silver nitrate. So in fact, some things that can happen are sometimes in the chemistry lab, you might not have access to pure enough water. So you might start your chemical reaction with tap water, for example. Well, tap water can occasionally have salt impurities, like a little bit of sodium chloride, or maybe some calcium chloride, or magnesium chloride, or and then you go and you add some sodium chloride solid to that water, and suddenly, instead of the concentration being the same as the sodium chloride concentration, you might have impurities from those other chloride compounds that might have been in your impure water. And so the actual amount of chlorine in your water supply is it might be different than what you had. And so that could have an effect on your chemical reaction. All right. So let's try experiment number 2, example number 2 here. We're going to write a molecular equation for the reaction between aqueous lead nitrate and aqueous potassium iodide. I'm just going to slide a little bit forward. Molecular equation. Okay. And then we're going to do some more. Okay, so let's write this one out. So here we have a molecular equation for lead 2 nitrate. So we need to write out the compounds, the ions present, and write the formulas of the initial compounds. So we have lead 2 nitrate, so that means lead is 2 plus here, and nitrate is NO3 minus, and it will be soluble. So I like to write them out as the chemical being broken down. So I am gonna do that. I gotta think about the charges on that nitrate. So nitrate only has a -1 charge, so lead 2 nitrate means that it will have 2 nitrates for each lead. And then this chemical is going to be aqueous, so it means in solution we are expecting to find a bunch of these lead 2 ions and a bunch of these nitrate ions. And then the other chemical we have is potassium iodide, which is aqueous. And so when potassium iodide is placed in solution, the solution suddenly contains potassium ions and iodine ions. I'm now realizing that this is the chemical formula for that yellow compound in that we were talking about in the previous example. That yellow rain was lead iodide. Oh well. I think I said lead chloride in the last video. Write the formulas of the 2 possible compounds that form from the ions. So we are going to do that little crisscrossing here. So we're going back to the original. We're going to do a crisscross of these 2. So what would that give us? That will give us a chemical reaction between the lead 2 plus aqueous plus iodine aqueous, and that should give us lead iodide. We're going to need 2 of those, and we'll have to go check our solubility rules, but you'll find that the solubility rules do say that lead is not soluble with iodine. We'll need 2 of those, and we are going to need we're going to do the potassium ion, which is aqueous, and we're going to react that with the nitrate ion, aqueous, and notice that these are actually going to be completely soluble, so we do get a chemical reaction, but it will be KNO3, and that will stay aqueous because nitrates are always aqueous things. Now notice that this is, if you did this correctly, this is a net ionic equation. So maybe we were doing twice as much work in the last example. Write the chemical equation and balance it. So the chemical equation here that we're talking about is to write the lead 2 nitrate, NO3, 2 aqueous is getting reacted with the potassium iodide, aqueous, and it is forming lead iodide, solid, and potassium nitrate, aqueous. And then we have to do some balancing here. So we needed 2 iodines, which means you need 2 of these KIs. And if you need 2 KIs, then you need 2 potassium nitrates made. Our spectator ions are all shown here. So these are our spectators. Ions, K plus, and NO3 minus. Okay, so this is a chemical reaction now where we're going to see if there is any precipitate formed. If we get a chemical reaction that is aqueous on both sides of the chemical equation, then we will have what is known as no reaction, and that chemical solution should remain clear in color. It should be translucent. There will be no cloudiness. So that's one of the ways that we'll be able to identify that in the lab. So let's do barium nitrate plus sodium 2CO3. Now, if you'd like, you could go through all the steps that we did in the previous one. So previously, we would look at what are the ions. I'm going to try to show you a sort of a quicker route, maybe. So let's do this kind of thing. We're going to do barium over here and realize that that's 2+, because each of the nitrates are on your periodic table of ions, I believe. So if you are forgetting them, forgetting what those look like, so I'm going to put those here, plus sodium ions plus CO3 to minus aqueous. Now I believe that carbonates are particularly insoluble in most compounds, so that's the one I'm keeping my eye on. And possibly I should have colored them maybe or something. So let's just color this one over here red. So I'm going to try to match up one of these red ones with one of the blue ones, or one of the uncolored ones, on the other side as a chemical equation. So let's see what would happen. Let's mix the barium with the carbonate and the sodium with the nitrate. And now I go and I check my rules. I know that sodium nitrate is aqueous because sodium and nitrate and the nitrate ion are both very aqueous chemicals reactions. And I'm going to go back up to my ion rules and look at that carbonate rule, because I need to check one thing. Most compounds containing carbonate ions are water insoluble. Exceptions are hydrogen, ammonia, and metals from the main group 1. Barium is from main group 2, so that would make barium carbonate a solid. So let's write out that in our, let's bring that back up to our chemical reaction and say this is barium carbonate, which is solid, and then sodium nitrate, which remains aqueous. And so this is a spectators. And then the barium carbonate is a precipitate. I don't have a balanced reaction yet, I don't believe. I only need one carbonate, so I only need one little fix here, which is to move this over to the right and add a 2. Put a 2 here, and there is 2 of these and 2 of those. Okay. So that's sort of a mixture of the two sort of approaches mixed together. I'm going to just do something like this too. I'm going to cancel this, cancel that and that, and show that it's barium 2+ aqueous. I really want to see a little bit of practice of the net ionic equation, because at some point we might try mixing 3 compounds together, and that's where it could be valuable to be able to write a net ionic equation. All right, so let's try some lead nitrate and some ammonium iodide. So here we have the lead nitrate. We're going to add some ammonium iodide. These are all aqueous solutions to start. So that means that we are having lead 2+ aqueous plus a nitrate aqueous, and there's 2 of them, plus an ammonia NH4 aqueous plus an iodine aqueous. That might even smell a little bit because of that ammonia ion. Don't like how that one ended up low. Okay, and so we carry that through. So we're going to be flipping partners here. So the positive ion is going to go with this other negative ion. This positive ion is going to go with this negative ion. And so let's see how that looks. That's going to be lead, iodine. We're going to need 2 of those. And add that to an ammonium nitrate. And we go and we check out some rules. We find that ammonium nitrates are soluble. We find that the lead iodide is not. We need 2 of these to react so that we have enough iodine to complete the chemical reaction and to use it in sodium, the nitrate. And so then we write our final chemical equation up here, our molecular equation, I guess we can call it. Oops. Yes. Good. And maybe we'll label our spectators. Spec. And this is our precipitate. PPT for precipitate. Okay. That was kind of a boring one. We didn't get a chemical reaction there. So let's see if we can get 1 more, 2 more here, and see what happens. We got our copper sulfate, aqueous. We got our sodium 3-phosphate, aqueous. And hopefully we're getting the point. So I'm going to just do the flip-flop with myself. Here I'm going to mix a copper with a phosphate. So this is where it might be valuable. This, see now, as soon as I said it, I was like, whoa, whoa, whoa. This is actually a tricky one because copper has a lot of different valence states. So it could be copper 1, it could be copper 2. And then I don't always remember what sulfate is, so I can go double check that one as make sure it's 2 minus. And then I got 3 of these sodiums to deal with, and they're aqueous, of course. And then I have a phosphate, which I have to go check and say, oh, that's a 3+ ion. Okay. All right, so let's see what we get here. We get a copper mixed with a copper 2+ with a phosphate 3-. So that means I'm going to bring the 3 down here. I'm going to do a bracket and put a 2, and then I have to go check my phosphate rules. I guess I could have made the other compound first and checked. And phosphate's in that same rule number 7. So I know that it's going to be solid. It's not going to be it's going to precipitate out. Okay. Just move everything over a little bit to give myself a little space. Sodium is a group 1 metal, and it's in that same rule, but it would be soluble because it is a group 1 metal. So the sulfate remains soluble. And we can double check some things. Let's think about, we're going to have to think about that balancing act here. We need 3 of these, it looks like, to balance the copper. But then we're going to need 2 of these phosphates, which means we're going to end up with 6 of these. Oops. We're going to make, well, let's maybe do, I'm going to do the balancing when I put in my final form here. 3 PO4 2, and that's the solid. And I'm going to put a 2 in front of there. That's going to give me 6 of those. I think that's going to be okay. I'm going to put that 3 there, plus 3 of these sodium 2SO4 aqueous. Yeah, that works. Okay, 3 there. And then that means that I'm going to get 6 of those and 2 times that, so that's going to be 2 of these, and I'm going to get 3 of these sulfates. Okay, great. So that's this is my ionic equation, ionic. This is my molecular equation, molecular. If I wanted to write the net ionic, then I would cancel out anything that's on the aqueous side. So I'd cancel out this with this and this, And my net ionic is going to be 3 coppers plus 2 phosphates. Gives us copper 3 PO4 2. And that is a solid. And that's my precipitate. Okay. So let's try this very last one. We've got a cobalt chloride mixed with a potassium hydroxide. So that means that we are mixing cobalt chloride aqueous plus a potassium hydroxide aqueous. So that gives us a cobalt that has a 2+ charge plus 2 chlorine minuses, also aqueous, plus 1 potassium aqueous, plus hydroxide aqueous, and that is all going to form together. So mixing pairs here, a cobalt hydroxide plus a potassium chloride aqueous. And so let's go find the hydroxide rules. Most compounds of hydroxides are water insoluble. Exceptions are metals of the main group 1 and of compounds between potassium, strontium, and barium and ammonia. Okay, so then that means that it is insoluble. So this is in fact one that's not exactly what I was expecting. I thought there'd be one trick question in here, but there is not. So that's cobalt hydroxide 2, and that is our insoluble precipitate, and potassium chloride aqueous. Okay, I'm going to push you a little bit. Let's try a couple of try 2 new questions, 2 sort of extreme questions. First one is going to be a trick question. So I'll show you how that trick question can work. So let's take the similar setup to the last question, except we're going to replace it with strontium chloride. Okay. Plus potassium hydroxide. And see what happens. So here, the strontium chloride, strontium 2+, aqueous, plus the chlorine minus, aqueous, plus the potassium, aqueous, plus the hydroxide, aqueous. Put that into the ionic equation, and we will find the formation of strontium hydroxide. Looks a lot like what we just had, except when we go check the rules, and I've already ruined the surprise. Where did that rule go? Okay, right here, we see that strontium is an exception. So strontium is not soluble, it is aqueous. So for this question, and we get potassium chloride, which is aqueous, both of these are aqueous, so they could actually be better written as strontium 2+ aqueous plus OH minus, or we don't have to put brackets on it, of course, aqueous plus potassium plus chlorine, and you can assume that they're aqueous. And so what do we do when we do a net ionic equation? Well, we cross out the common ions to both sides. Well, wait a second. If you cancel everything out, you are left with an ion equation. There's no net ionic equation. So that means no reaction. No reaction. And so there's your no reaction example that they kind of hinted at. So when you go to the precipitation reactions in the practice, please watch out for those no reaction examples. I'll leave a more complicated example that I'm thinking of in my that's percolating in the back of my mind. I'll leave that one for a little later, I think, and let you work on these for now. Good luck.